been exploring the chi-square distribution in our investigations of the Hardy-Weinberg equilibrium theory. In our exercises, we use the chi-square distribution, and I'm showing the Wikipedia page for the chi-square distribution, and just wanted to read to you what this distribution is all about. Before I read to you, though, what I wanted to do is point out that the chi-square distribution is shown on the right side here. And what this is showing are the chi-square distributions for different degrees of freedom. So the chi-square distribution is controlled by one parameter called k, which we call the degrees of freedom. And when k changes, the shape of the chi-square distribution changes. In our explorations of Hardy-Weinberg, we calculated the Pearson chi-square test statistic. Let's say the example resulted in a 6. And then we found where does this particular value fall for a chi-square distribution with a specified degrees of freedom. So for example, if our degrees of freedom was 1, then we would say that a 6 is a pretty unlikely value because there's not many more values that score to the right of the 6. Much more of this curve's area is below 6. And so we would conclude that this is a unusual or a rare kind of event. So it's a number that's not common in this particular distribution. It's rare to get a number of 6 or above. In contrast, if our degrees of freedom was 9, shown in red, we would have a completely different conclusion about our test statistic and where it falls. Now, we used some Excel built-in functions to build our chi-square distribution, and if you wanted to prove it to yourself, you can use Excel and generate these distributions yourself. Here, though, we're going to build these distributions through a simulation, and hopefully this will just remove some of the mystery about where this distribution shape comes from. Our sentence of interest is really this first sentence. In probability theory and statistics, the chi-square distribution with k degrees of freedom is the distribution of a sum of the squares of k independent standard normal random variables. And this distribution is used throughout many investigations, and so it's a really good one to get a handle on. So let's keep this in mind as we return to our spreadsheet. Here's the spreadsheet we've been working with. It's on the tab called chi-square distribution, and I've shifted a few of the cells around to give us a bit more space. In the last videos, we plotted a chi-square distribution with 2 degrees of freedom, and we were able to let you change the shape here by just entering a different number in cell C2. And in cell C3, we enter our observed Pearson chi-square test statistic, and we use this chi-square distribution RT function to tell us where does this number 6 fall with respect to the rest of the values. So for example here, if we find the number 6, we see that 30% of the area under this curve falls to the right of 6, and then 1 minus this value falls to the left of 6. And we use this value to draw conclusions. So the theoretical chi-square is used to help us find where our observed test statistic falls, and then make some statements about our data. Is the population in Hardy-Weinberg or not? Now, returning to the Wikipedia example, it said that in order to build a chi-square distribution with, say, 2 degrees of freedom, we need to draw independent standard normal random variables. And the fastest way to talk about this is just to plunge right in and draw some of those variables from Excel. Here we set up a list of variables from -4 to +4, and we're going to use a function in Excel called norm.s.dist, and this returns the standard normal distribution. It's a distribution that has a mean of 0 and a standard deviation of 1. When we open this dialog box, we're going to be asked for two arguments. The first argument is the value we draw, which it's calling z. We've got it labeled here as x. It doesn't really matter for the purposes right now. And we want the exact probability, the probability density function, so we're going to enter the word false and then copy this through. And what you've seen is we've pre-populated our sheet so that this graphic is charted out. So we have x on the horizontal axis and we have probability density on the vertical axis. And you can see that the distribution itself is centered on 0, which is in fact the mean of the distribution, and it has a specific shape. This particular distribution has a mean of 0 and a standard deviation of 1. For the purpose of creating our chi-square distribution, we need to draw standard normal random variables from this distribution. And we can use another function in Excel to do this for us, and it's going to have this inv ending at the end of the function. So this is norm.s.inv. And our probability here is just going to be a random number. We've set up 1,000 trials down column H, and now we're going to be drawing variables from this standard normal distribution. So my first variable that I drew was 2.2, way over here. The next one was -0.71. That's someplace in here. So you can see that drawing this second value is much more likely than drawing a 2.2, which is over here in the tail. To prove to ourselves that these 1,000 trials end up with a mean of 0 and a standard deviation of 1, we'll enter the equations for the mean and standard deviation in cell G2 and G3. The mean is just the average function, and we're going to be averaging the results down column I. And the standard deviation is STD, and you can start typing that, and you'll see that there are two variations for this particular function. The first is considering the standard deviation for a population, and the second is considering the standard deviation when you draw a sample from that population. So we're going to choose that because we're just drawing 1,000 random samples from an infinite population. And our data, once again, is listed down column I. So you can see that the mean is close to 0 and the standard deviation is close to 1 from our random samples. And if we press F9, we'll get a whole bunch more of those values, but each time we're drawing them, we're simulating 1,000 new samples, and each time the mean is close to 0 and the standard deviation is close to 1. These are called standard normal random variables, down column I. They are independent of each other, meaning that the draw that resulted in trial 1 has no bearing on any other trials. They're completely independent. To build a chi-square distribution, we need to gather a sample of these independent standard normal variables, and we need to square them and then sum them. If I were to build a chi-square distribution with 1 degree of freedom, then I would just need one set of squared random deviates here. Now what's going to happen if we square these values? If we just square those values, then we are going to end up with a column that's full of positive numbers. And so that's why the chi-square distribution starts at 0 and goes out. It does not include any negative values for x at all. If I were to do a histogram and convert these to probabilities, then I would be graphing out a chi-square distribution with 1 degree of freedom. To get to 2 degrees of freedom, I need to have 2 sets of these. So I'm going to take a second set, and I'll just move this graphic down over here and show you some more of the spreadsheet setup here. So to get a second set, we're going to repeat our value here, and now we have a second set of trials, and each one of these, once again, is a standard normal random variable. These are now independent of each other. Each of them has been squared, and now we're going to sum those. And now we can graph a frequency histogram of these sums of these squared, independent, standard normal, random variables, and that would generate our chi-square distribution with 2 degrees of freedom. Now you'll need to give us a little bit of slack here because we're not going to be generating exactly this distribution. We've generated only 1,000 trials, and we'll end up with something that looks somewhat like this distribution, just enough to give you a good feeling for where it's coming from. Now to graph these results here of our 1,000 trials, we're going to use the frequency function in Excel. And the frequency function is a different kind of function. It's called an array function, and you enter it differently than you do other equations. In order to enter an array function, you need to select a whole set of cells at one time, and then find the frequency function. So we're going to find frequency, and the first argument is the data. So our data array is stored down column K, and our bins array is this value here storing the values for x. So what x is doing is we're trying to summarize how many of these 1,000 results were between 0 and 1. We'll store that entry here. How many of these results down column K were between 1 and 2? We'll store that result here. Now, don't press OK here. If you've pressed OK, you've already made a mistake. Because this is an array function, you need to press Control plus Shift plus Enter in order for this function to work. And I like to go up into my formula bar and then press Control Shift and Enter and fill them in that way. At this point, we can grab our data and simply do a quick scatter graph and compare our distributions. So what you're seeing here is roughly the same shape, and if we converted these numbers into probabilities by dividing by 1,000, then essentially what we'd be doing is rescaling this vertical axis to make it more like the probability density. I'm going to leave that here for now and just let you ponder how this and think about how this distribution was made, and to return to our Wikipedia definition. So I'll read it once again. In probability theory and statistics, the chi-square distribution with k degrees of freedom, so here we've built a 2 degrees of freedom distribution. It's the distribution of the sum of the squares of k independent standard normal random variables. It's one of the most widely used probability distributions in inferential statistics. And we've used this to draw conclusions about whether populations are in Hardy-Weinberg equilibrium or not. If we wanted to draw or make a chi-square distribution with 3 degrees of freedom, what would we do? Well, we'd add another column here, and we'd copy this formula over. So we draw another standard normal random variable, square it, and then include that in our sum. If we wanted to have 4 degrees of freedom, we would have 4 columns of x, and so on. So hopefully this gives you a better understanding of what the chi-square distribution is and how we use this distribution to draw conclusions about populations, such as whether they are in Hardy-Weinberg equilibrium or not.